record. So today we're going to wrap up the chapter with our discussion of this idea called the electric field. I started talking about it yesterday. And the idea of an electric field is that, well, if I have two charges around, or let's say a positive and negative, I can compute the force between them, right? They're going to attract each other, right? Let's say this is charge 1, this is charge 2, right? So charge 1 will have a force from charge 2 on 1, and then charge 2 will have a force from charge 1 on 2, okay? But what if I take this charge and start moving it around, right? You're going to have to recompute this formula over and over and over again. But the idea is that let's just go down here. If we just have a single charge around, right? What if we come up with this idea that, well, I can make up this field, okay? And there's some arguments actually, if you are interested in like kind of like the, I don't know if it's called metaphysics or like the philosophy of physics or philosophy of science. Some people feel that the field with the two E's, that the fields themselves are actually more fundamental than the charge. And some people argue that the charge is actually the real thing we can see. But then, right, you don't actually see anything without these fields. And we're going to see what that means. And especially, I'm using the word see for those of you who might know this material, that this word see is actually a very interesting word. Okay, the idea is that, well, if I have a positive charge, right, and I place a positive charge here, right, it's going to feel a force pushing the blue charge from the red charge, right? Okay, but this red charge can be placed anywhere, so I don't have to tell you what that red charge is, right? This blue charge is going to emanate a field whether or not that red charge is around, okay? Even though technically you can't really see it yet, okay? But what happened is that, well, what if your center charge is actually a negative charge, right? So in this case, the red charge is actually negative. If I place a positive blue charge here, right, QB, right, instead of repelling it, it's actually going to attract it, right? So the idea of this field is that if you were to place a positive, and the textbook call it a positive test charge, meaning the field themselves don't have this, the field themselves starts off with just one charge, and you're just drawing all these, arrows towards it. But if I was to place a positive charge there, what would happen, right? Is it going to be attracted to the center or push away from the center? And that's the direction of these electric field vectors that you want to draw, okay? So in this little quick example here, right, more solid example, right? We have some Q, and I really don't like the book using these prime notations, but some, but it does, right? Where you have a charge, right? If you have a charge Q and a charge Q prime, if they're both positive, they're going to push each other apart, right? So the electric force between them, right, is calculated from what we learned last time from Coulomb's law, right, with this capital K, which is the Coulomb constant. The book calls it the electrostatic constant, which also sometimes confusing, right? But I would just call it the Coulomb constant because it's directly related to Coulomb's law, even though it's not officially called that, okay? And you can call it either way, big K. And it just tells you, well, what is the force on it if you have these two charges divided by the distance between these two charges, right? So when we start doing electric field, it actually kind of do a little switcheroo on you, okay? Instead of using the electrostatic constant, okay, they're going to switch you over to this thing called the permittivity of free space, epsilon naught. So this is named epsilon. Okay, it's just kind of a fancy Greek letter for a Greek name for the letter E. Okay, and the way so this, when you type it, is like, it looks like this, but usually when I write it typed, right, usually when I write it, people just will write it like this, kind of like a little squiggly E, okay? Right, and that's epsilon naught. And the naught will come into use when we start learning about index of refraction. But so this is actually a recasting of the same variable that we learned already, the electrostatic constant. So they're going to define epsilon naught as 1/4 pi divided by the electric constant. Okay, and you would think, when I first learned this, like, why the hell did you do this, right? Why do you want to keep track of yet another Greek letter, right? So it's kind of a stupid thing, but it turns out this 4 pi is going to come in useful, because the 4 pi is actually an extremely neat thing, because the surface area of a sphere, right, is actually 4 pi r square, and that's going to come in useful. And there is a reason for doing this. Okay, so just the physics people who are writing these textbooks are not just making up Greek letters just to I shouldn't swear, mess with you guys, right? Okay, so with this definition, if you solve this for k, right, k is going to be 1/4 pi epsilon naught. So what we can do is that, oops, if I can get my tablet to go up, right? Replace this k constant with the version with 4 pi epsilon naughts in it, okay? So rewriting Coulomb's law, it looks like this instead. So this basically gets, the k got replaced by that, okay? I'm going to use this for electric field, okay? So this tells you that, well, it's the same thing as Coulomb's law, but now, right, instead of the nice little letter k, now you have to type in 1/4 pi epsilon naught, and epsilon naught is 8.85 times 10 to the negative 12. So it's a small number instead of a big number, right? Remember, the Coulomb's constant was a big number, it was like 9 times 10 to the 9, right? 9 billion, right? This is a very small number, okay? Right? 10 times 10 to the negative 12, okay? What we're going to do is that, well, the idea is that, well, if we have an electric force between the two, if I remove this charge, what would happen, right? Right, what would happen if I remove that charge, okay? So now if I don't have that charge there, in order for me to compute the force that would have happened if you place the charge there, I'm doing this little rigmarole, okay? The electric field is supposed to tell you what is that force, okay? Right? So what happened is that you basically take the force equation and you divide it by the test charge, Q prime, okay? So if you do that on both sides, that's actually the definition of the electric field, which is also a vector, right? Force is a vector, electric field is a vector, okay? These two cancel each other, and we can rewrite the formula to calculate what the electric field at a particular point is, even if we don't know the charge or the position, right? Because this charge can be over here, over here, over here, over here, right? It can be anywhere, right? Okay. So the only difference between the electric field formula and the force formula is that there's no Q prime, okay? Is gone. Okay, that makes sense? Okay, I know we're doing like a bunch of little flip things, the logic behind it, okay? Okay. So the electric field seems like just this made up thing, right? And as I mentioned, right, when you have two different charges around, right, you can calculate what the force is. But if you only have one charge, that charge still has an effect on the environment around it. Just think of electric field as these electric charges modifying space and time around it itself, okay, which is sort of a neat thing, okay? Even though we don't see its effect, it's actually changing the space around it, okay, right? And in order for us to describe electromagnetic field in the future, also known as light, this is how we see, okay? We need to have this concept of fields. If we don't have this concept, then we cannot actually describe electromagnetic fields because you don't have this idea of a field, Okay. So for a point charge, right, as we stated, and for if it's a positive charge, the electric field always goes away from it. Okay. And so if you want to calculate the electric field at this point, right, you have to figure out what is this distance and the direction, right? Because electric field is a vector, so we need to know the magnitude and the direction. Okay. The magnitude comes from just 1/4πε0, the charge, which is the one at the center, divided by r squared, right, the distance out. And then the direction comes from, well, where your positive charge is pointing to where you want to actually calculate the field strength at that point. So this is one of the confusing things, is that there's nothing there, right? But you can still calculate the electric field at 0.1, 0.2, 0.3, wherever you want. You can, you can have 0.4, you can have 0.5, right? And these electric field will point away from the source of the charge, the source of the field. Okay, if the field is negative, right? But in the case that if the charge is negative, all these field will point towards the negative charge, right? And that's because if we put a positive test charge here, it will attract it, right? As opposed to repel it, right? In the case of a positive version, if I put a positive charge here, it'll get repelled, right? Okay, so make sure you have a firm connection between force, the electric force, and the electric field. They're essentially the same thing, okay? But electric force, you can only calculate if you have two charges, right? Electric field, you can calculate with a single charge, okay? All right. So an easy way to remember this formula is that, well, if I want to relate the electric force on a charge q prime, right, and relate it, if I want to figure out what is the, if I have put a charge q prime here, what will be the electric force on it? It's just that charge times the electric field. Okay, that's a very useful thing to have. Okay. Okay, a lot of times you actually do the other way, but yeah. So the electric force on something is just that the amount of charge you place into that field times the strength of that field. Okay. All right, there's multiple examples that I suggest you guys go through in the textbook, right? But let's see, I think we have time for this last example also. But let's go through a little stop to think, which is also in the textbook, right? What they want you to do is, well, we can't do the rank order thing because we don't have we can't have multiple answers. But we have these 4 different situations, A, B, C, D. Okay, well, four different positions. And next to it are these charges, okay? Okay, and at field point A, you have a small amount of charge at a distance r from it, okay? At field point B, you have twice the amount of charge, right? At the same distance, right? These are the same, okay? At field point C, right, you have a small amount of charge, but twice the distance, okay? And then at situation at field point D is twice the amount of charge and twice the distance, okay? So let's do just another raise of hand situation where can we figure out which letter has the biggest electric field? Which point, A, B, C, or D? They're kind of disconnected from each other. Okay. Think about this for a couple of seconds. And does anyone think it is A? Anyone thinks it's A that has the biggest electric field? Okay. Who thinks it's B? Okay. Great. Most of the class. And should I go through the rest? Because I think most of the class probably agrees it's B. And I think I do also. Right? Remember that the electric field is calculated with this 1/4πε0 thing, but the relevant quantities is the charge of that electric field divided by r squared, right? And r hat direction, right? So the bigger the charge, the bigger the field, but the smaller the distance, the bigger the electric field also, right? It decreases as r squared because, right, r squared is in the denominator, okay? Okay, so indeed this is going to be B. Okay. What about number 2, where we're trying to figure out which one has the smallest field? Okay. Okay. So we know that B has the biggest one. Anyone thinks that A is the smallest field? Okay. Anyone thinks is C? Right. So most of you guys also think that's a C because this has the smallest charge, small charge, and also large distance, right? Okay. Those two combinations, right, make the electric field the smallest possible. Okay, so that's actually C. Okay, this one's pretty close, right, because it has a long distance, but it has twice the amount of charge. So actually, the electric field strength between C and D, right, C is actually twice as strong as D, right, just because you have twice the amount of charge making that electric field. Okay, so let's work through an example. Yeah, cool. A and B are, yeah, that's actually a very A and D. Yeah, that's actually an interesting question, right? So that's probably what I should have asked in this situation, right? So in A, you have one unit of charge at 1 times the distance, right? At D, you have twice the amount of charge, but twice the distance, right? Which one has a bigger effect on electric field, the amount of charge or the distance? Mathematically, I'm sorry? The distance, right? So if you double the distance, what happens to the electric field? Does it go down by a factor of 2 or does it go down by a factor of something else? By 4, right? So this actually is like A is actually going to have a stronger field than D because of that R square situation. Okay. All right. Good point. Okay. So let's do a quick, quick as in me struggling with math type of situation, right? Let's work on this problem. It's actually out of the textbook. Problem in chapter 22, problem 33, okay? We have a 12 nanocoulomb charge located at the origin, okay? So I'm trying to get the information here, right? And usually a lot of times it's nice to just start making a drawing, even it may or may not be needed, right? So I'm gonna draw an X and Y axis right away. Okay. And the problem is telling me that I have a 12 nanocoulomb charge. You're gonna even label that as Q equals to 12 nanocoulomb, okay? And what they want you to do is calculate the electric field at these various positions, 3 different ones, okay? I'm gonna do 2 of them. We'll just skip the third because we don't need to see me struggle with math as more than necessary, because the third one is actually pretty similar to the second one. Okay, so the position of field point, I'm going to label this 1, 2, and we're not going to do 3, but we'll label that 3 also. Okay, so field point number 1, right, is located at X equal to 2 centimeter, Y equal to 0 centimeter. So this is going to be around here, right? That's field point number 1. Okay. 5, 0 in centimeters. Field point number 2, right, is actually negative in the X direction. So it's going to be left here. And then positive in the Y direction. So it's all the way up here. Okay, that's field point number 2. Let's label that 2. Oops. Okay. That's -5, +5 in centimeters. Okay. So I'm just looking at this diagram, right? I can probably figure out what direction, at least, where the electric field is going to point, right? So for point number 1, which direction do you guys think the electric field is going to point? Up, down, left, right? Positive X, right? To the right. Okay, good. That's the direction of electric field at point 1. Okay. What about up here? Which way would the electric field point up there? Up, down, left, right, at some angle. You can just say which way. You want to point, you can just point your arm in whichever way you think it's going to go. Oh, yeah, top left to you guys. Yeah, great. It's going to point this way, right? That's electric field 2. So electric field 1 should be not too bad because it's only in the x direction. Electric field 2, we're going to have to deal with some vector stuff, right? Because it's going to be, it's at an angle, so it's going to have some x component, some y component that we have to deal with. Okay. Nice thing about the geometry of this problem, right? Since this is -5, +5, right? The length of this is same. When you have two legs that are the same in a triangle, what is the angle there? Anyone want to venture a guess? 45, right? 45 is halfway between 0 and 90, right? Okay, so right away, we don't need to do some trig function to figure out what that angle is, okay? So the concept we're going to try to do is, right, going to compute the electric field vector, because they're going to have to deal with vectors, using the equation, right, at various field points. So each of these points are called field points. Okay. Right. So the equation that we're going to use to start solving this, right, is just the electric field formula, 1/4πε0, right? Q divided by r squared times r hat. Okay. That's where the calculator comes into use. Okay. So in this case, we can plug in what 1/4πε is, but do we know what the value of 1/4πε is without punching it in a calculator? I'm sorry? Well, right. Epsilon naught is 8.85 times 10 to the minus 12. I think this has units of, let me go look up. Where is it? Coulomb square, newtons per newtons per meter square. Okay, it's kind of upside down from. Go back, right? Square, Newton square per meter square. Okay, so let's just do this as an exercise, right? So if I punch this in the calculator, right? If I calculate one, if I plug this in here, right? 1 divided by 4 times 3.14 times 8.85 times 10 to the negative 12. And it happens, right? 1/4πε0 is equal to 8.99 times 10 to the negative positive 9, right? And this has units of newtons meter square per coulomb square. Does this number look familiar to anyone? That's actually K, right? So whenever you have exactly 1/4πε0, don't punch it in your calculator to calculate that. Just write down, just know what the K is. That's why the electric static constant is still around, because it's just convenient, okay? Even though fundamentally it's actually a less useful constant, okay? So let's find the electric field at point number 1, right? So the R vector, right, as you stated, right, it's going to be in the x hat direction, okay? But what is the magnitude of that? How far apart is it? It's 5 centimeters, right? That's actually 0.05 meters, right? Let's put the units in the back there, okay? So the magnitude of R is 0.05 meters. So we can have that plugged in there. And we know the charge, right? What is the charge? 12 nanocoulombs. So remember, a nano is 1 times 10 to the negative 9, right? Put that in there. So electric field at point 1, okay, it's going to be 8.99 times 10 to the 9, okay, times, okay, and everything is in SI units, so we don't have to do any unit conversions. The charge is 12 times 10 to the negative 9, right? And then R is 0.05, okay? It's going to have meter squared, but we know that, let's just write in the units for now, okay? Since we're doing this the first time, okay? Coulomb square, so this will be coulomb, this will be meter square, okay? Okay, so those are the units. I'll put a little bracket around it, okay? So you can see that the meter square cancels out with the meter squares on the bottom. One factor of the Coulomb cancels out, but not both of them. And this is going to be in the I hat direction, right? Because that's direction of R. Okay. Another neat thing is that, well, you have the 10 to the 9 here. You have a 10 to the minus 9 there. When you multiply those two together, you get 1. Yeah, question? Is so epsilon naught is 8.85, right? But we're not using, we don't want epsilon naught in front, right? We want 1 over 4 pi epsilon naught, right? If you calculate 1 over 4 pi epsilon, you get this, you get the electric constant again, right? Okay, so 8.99 times 12 divided by 0.02 square. Okay, so the electric field, go back to black, right, is 4.3. Okay, so we're doing this 3 sig figs, 3.2 times 10 to the 4. The units that are left over is a Newton per Coulomb. Okay, right, so that's the electric field, newtons per Coulomb. Okay, so that's part A, but at field point 2, right, it's a little bit more complicated because we have to deal with the 2-dimension thing. Okay, so electric field at point 2 is going to have some I hat direction, some J hat direction. Okay, and we can calculate that using, well, instead of writing 1 over 4 pi epsilon naught, I'm just going to write K. Is that okay for both of them? Right, because that's exactly 1 over 4 pi epsilon naught. Mm-hmm. Uh-huh. Right, R hat tells you the direction of R, right? And we know that the direction of R is actually I hat. Okay, it's only in the X direction, right? And this, and yeah, it's a good point to point out, right? You can see that, you know, the electric field has to point in the X direction, right? And this one is going to be harder, right? We're going to have some weird. Yeah, R hat is the R hat, right? These hat factors tells you the, so let's say you have, let me just describe this way. At the origin, you have some origin here, and you have some position vector R. Okay, R hat, the R vector is the magnitude of R times R hat. So this is known as a unit vector. Okay, it has a length of 1 and it only tells you the direction information. Okay, R hat will not be because you have to specify, you know, is it in X or is it, so R hat basically just turn into either in the X direction or in the Y direction or combination of the two. So oh yeah, that's my mistake. Okay, that might be why you're confused because I didn't write the direction down, right? Okay. Right. So, oops. So once again, so we can just use the K instead of 1 over 4 pi epsilon naught. Then you will have to write the charge. The distance, as I remember a lot from last time, right, is different, right? So from the origin to -5, 5, right? This distance is actually using Pythagoras theorem, right? R is actually square root of 5 square plus 5 squares, both in centimeters. Okay, and we'll convert this to meters in a second. So basically, you get 5 square plus 5 square, oops, which is going to be like 7 or something like that. 2, okay, 7.07, and this is going to be in centimeters. If we write it in meters, 0.0707 meters, right? Because we want this in SI units. Okay. So this is nice, but we have to be careful about this directionality of it, right? Right. From the diagram up here, we know that the X component is going to point in the negative X hat direction, right? Negative I hat. The Y component is going to go in the positive J hat direction, right? Okay, so when we go back down to here, right, we know that this has to be negative and this has to be positive, okay? So let's do that computation, right? So replacing all the Q equals to 12 times 10 to the negative 9. And then R equals to this, right? And then K is 8.99 times 10 to the 9, right? We did all that calculations, right? Times 0.99 times 12 divided by, okay, electric field 2 to get the numbers. We know this has to be negative, okay? It's 2.16 times 10 to the 4. And once again, I didn't do the unit analysis in this instance, but we know that electric field should have units of newtons per coulomb, right? So we can actually just write down the units. This will be in the I hat. The magnitude of this is actually the same, but it's just in a different direction. It's per coulomb in the J hat, okay? So that's the whole answer. Okay. Any questions? Okay, not, I know I went a little long.